listeners. My name is Cliff Ratza. I'm the author of 2 ongoing series of novels, the Lightning Brain series, and its sequel, the Keeper series. In addition to being an author and a writing coach, I teach at universities and have a consulting business. Now, I have 2 rhetorical questions for our listeners. Why don't most people like math? And why are most people, even people like me who teach this stuff, usually afraid of numbers? Well, here are my practical, simple scholar answers. Most people don't like math because we think in terms of words and pictures, not in terms of numbers. Our verbal or linguistic ability is primal. When we see something, we immediately try to describe it using words, not numbers. And most people are afraid of math because they aren't good with numbers, at least when beginning to learn about math, because we don't know the vocabulary and the language of mathematics. It takes a long time to build this foundation. I go to many writing seminars, watch writing videos, and read relevant articles. And something shared among all literary types is a dislike for and an admission that they struggle when dealing with numbers. And there are smart people gifted using words. And why do they struggle? Because they never learned the vocabulary. And why not? Well, because math doesn't help them too much in their daily lives. I have read books and articles talking about these problems. One of the better books is Innumeracy, written by John Allen Paulus. And here's a representative summary of most reviews. Paulus is very good at explaining all of this, though sometimes with a hectoring, bitter tone for which he apologizes at the very end. He notes correctly that the public's failure to understand chance phenomena, statistics, probability, and the nature of many numerical assertions opens the way for all manner of belief and nonsense. Perhaps more important, it leads to distortions in the making of public policy. Well, that's why I'm making this podcast. Instead of blaming people, I flip the finger pointing by blaming mathematics. The title of this podcast is Why Math Should Be Our Friend, Why Numbers Can Be Helpful. And I will use my simple scholar approach, coupled with exhaustive study of mathematics as well as teaching for a number of years, including most recently grad business and biostats courses. So I think what I'm about to say should help all listeners. Authors and writers should like it too. Albert Einstein had one of the best answers when asked, what is the most important property of mathematics? His answer, compound interest. It's the 8th wonder of the world. He who understands it earns it. He who doesn't pays it. So let's tick off why mathematics should like us. Probability and statistics is the one combined area of math that can really help us on a day-to-day basis. Statistics is all about doing basic calculations, that's adding, subtracting, multiplying, and dividing, on a set of numbers, that's some sort of sample, to come up with something useful, like the average value, or a measure of how spread out the numbers are. So, think of stats as being the science of numbers. And here's the area in our lives that probability and stats can help us most. in games of chance for computing the odds of winning. In healthcare, for measuring the odds of getting sick, think COVID-19. In elections, for figuring out ahead of time who might win. And when investing, for figuring out how much we might get. I've already given a simple definition of stats, but what is probability? Probability is the branch of mathematics concerning numerical descriptions of how likely an event is to occur, or how likely it is that a proposition is true. The probability of an event is a number between 0 and 1, where roughly speaking, 0 indicates impossibility of the event, and 1 indicates certainty. So, probability is a theory that supports statistics. We use a graph called a probability distribution that shows how probability is spread over the set of all possible values. That's sometimes called all the events that might occur. Here are the rules. Probability is never negative, and the sum of all the probabilities must equal 100%. Every event has a complement, and that's everything that didn't occur when that event occurred. And the probability of the complement equals 1 minus the probability of the event. And if events are disjoint or independent, the probability of event A or B occurring equals the probability of A plus the probability of B. Now, there are two important parameters that describe every probability distribution. Its central value, which is the mean or the average, and its spread. That's its standard deviation, or how the numbers are spread out. There is a most important probability distribution, the bell curve, also called the normal distribution. I'm sure you've seen its picture and know why it's so important. Many events we observe in the real world follow this distribution. Here's a great example. Take the population of females in the United States and measure their heights. The distribution of heights follows the normal distribution. And here's what I think is the most amazing property of the normal distribution. Even though there are many other important probability distributions, the normal distribution is their limiting or asymptotic distribution, which means they all look like the normal distribution when the sample sizes get big enough. And we use probability and stats when doing statistical testing. Here's what it is. Take a sample, like some people out of a city. Measure a particular event, like COVID-19 infection, and calculate the average value. In other words, what percent have COVID-19? When you do that, you now use a probability distribution called the sampling distribution of the sample mean. What a mouthful of words. I have to review my understanding of what it means every time I teach my grad stats class. Here's what it is. Take a sample of a particular size. Call it N. Well, as you take more and more samples of that size, the probability distribution of the sample mean is the same, and assume it's normal, and has the same mean as the original distribution, but a smaller standard deviation. Divide the original standard deviation by the square root of n to get the smaller value of the standard deviation. And once we've done all that, we can calculate a confidence interval. All my students struggle to understand what a confidence interval is. So let me give you the simplest definition I can. You pick a confidence level like 95% and use that value to calculate an interval centered on that sample mean you get from your experiment. And then you can say that 95% of the time your actual sample mean will fall inside that interval. But avoid making the mistake everyone does it first. This does not mean that there is a 95% probability of the true mean falling inside this interval. You don't know, because that probability is either 0% or 100%, and you don't know. The probability in stats I've been talking about so far is called classical probability in stats, and is based on repeated experiments, like flipping a coin or rolling dice. By the way, dice is the plural of the singular word die. But there is another branch of probability in statistics called Bayesian Statistics, which allows us to use subjective or best guess prior probability estimates. The math details gets involved, but the final rule is pretty straightforward. The posterior probability estimate equals the prior probability estimate times the likelihood function. All this extends Bayes' theorem, which uses conditional and marginal probabilities. I get confused by it, and I have to review this stuff thoroughly every time I prepare to teach. But Bayesian stats is important. For example, volcanologists take seismic readings near volcanic hotspots to calculate the probability of an eruption. But you can't run experiments. An eruption, if it occurs, is a one-time only event. I'm just about done. Only two more reasons for me to go over. The first has to do with elections. Pollsters take samples of voters and from it determine what percentage will vote for candidate A or for candidate B. And then they will calculate a margin of error for a stated confidence level, often 95%. If the difference, according to the sample, between the percentage for candidate A and candidate B falls outside this MOE, or margin of error, then whoever has the higher percentage is likely to win. But if the difference falls inside, the election is too close to call. And now to my final reason, which has to do with investing. All you need to know for starters is the difference between association and causation. Association simply means the two things are correlated. Here's an example. People who drink red wine tend to live longer. In other words, drinking red wine is positively correlated with living longer. But do you think drinking red wine actually causes a person to live longer? If you do, then you believe that drinking red wine is an explanatory variable telling us why people live longer. And if you do, you can use regression analysis to come up with an equation that'll predict how long you'll live if you consume a certain amount of red wine. The equation contains two parameters, alpha and beta, which in CAPM, which is the capital asset pricing model, which is found in MPT, which is modern portfolio theory. Beta is the correlation of a particular stock's return with the overall market, and alpha is the active or excess return over and above what the market does. And by the way, there's an investment website called seekingalpha.com. Seeking Alpha is a crowdsourced content service for financial markets. In contrast to other equity research platforms, insight is provided by contributors, including a base of investors and industry experts, rather than just the stats of selling. In other words, Seeking Alpha is looking for stocks that beat the market. Very hard to do because Wall Street is supposed to be an efficient market, but not always. The trick is knowing when or when not. And that's all. If you understand the above, then there's a high probability that you know more than most people why mathematics should be our friend. Thank you for listening, and bye-bye until next time.